So good day everyone, and welcome to the 6th day of study group session. Today is going to be an exciting day. We are going to finish all the material necessary for your exam tomorrow. Plus we'll do some revision. You all will get a big picture. So it is going to be an excellent day. Before we get into the interesting stuff, I want to clear up a few definitions. So we are on ordered pairs and direct product. This is 4.3. This is very straightforward. Definition: let H and K be groups. The direct product of groups H and K denoted by H times or cross K, but it's really H direct product, right? K is the group of elements of all ordered pairs HK, where H is in H and K is in K with operation dot, defined by H1 comma HK dot H2 comma K2 equals to K1 K2 comma, that's H1 H2 comma K1 K2. So basically just multiply the elements. That's just a definition. You all will meet it up when you start to do your course, but I just want to define it here. Anybody has any questions on that? Nice. Note that this is different from the normal dot product, right? Remember in vectors, if we have A dot B, if we have A, B dot, vectors, 2, 3, this is 2A plus 3B, yes? But this is a value, this is a scalar, yes? Whereas here, we have A, B cross 2, 3. This gives the ordered pair 2A, 3B. You'll see the difference, right? Nice. Next would be in the notes, you all may see this. So H, what is the difference between this? So this is what this says. H is a subgroup of G, yes? So what does this say? H is also a subgroup of G, right? But just as in sets, we have subset and we have subset and we have proper subset. And this one gives the, if A is a subset of B, then you could get B being a subset of A in this case. But if A is a proper subset of B, that means that there exists an element in B that is not in A, yes? So it's the same thing. So this one gives the option that G could also be a subgroup of H, whereas this one doesn't give that option, yes? This triangle is normal subgroup. So this says the same thing. So H is a normal subgroup in G, whereas this one says H is a normal subgroup in G, but there is the possibility that H could actually be equal to G. Everybody's okay? Nice. So I just thought I'd mention that because in the notes you would see differences. I just want to make sure you're all on the same page and don't think they are typos. Yeah? Isomorphism theorem is also called the homomorphism theorem. You all seen that, right? Nice. Let F be a function. Let F be a homomorphism from G to H, between groups, with kernel K. Then K is normal in G, so the kernel is always normal in G, and the factor group of G by K is isomorphic to G bar. The note is what is important. So note K is the kernel of F, yes? G bar is the range of F. Thus, it could be stated as the domain of F over the kernel of F is isomorphic to the range of F. You all follow? So just remember F is what? F is a homomorphism, right? Which is a mapping. full stop, right? Mappings, we're talking relation, we're talking functions, yes? So if we have a mapping f from A to B, and A has 1, 2, 3, 4, and this has A, B, C, D, E, and let's just say this is my mapping. If f, so the isomorphism states, now these are not groups or anything, right? It's just to give an illustration, right? It says that the domain of f, which in this case is A, yes, domain over, I'll just put one of these as E, right, for the identity, yes? In fact, I'll just put 2. Over the kernel of f. Now in this case, the kernel of f are those elements in the domain that are mapped onto the identity in B, yes? The identity in B is E. So 2 and 3 maps onto E, yes? So 2, 3. So this is isomorphic to the range of f. So what is the range of f? The range of f are those elements that are mapped onto. Yes? So it will be A, E, and D. So notice, oh look at, no, this E, let's just put this as f, right? You follow? So f is not here. So it doesn't say that this maps onto this. It says that it maps onto the elements that are used. Yes? So that is very important. So remember it. Domain over kernel is isomorphic to range. Yes? These 2 examples, and they work really nice. I mean, you won't gain any great knowledge in mathematics, but you will understand the theorem. You'll follow? And it does a lot. So I have these 2 sets. Now, before I go into it, I am putting a star here, which means that this is an aha moment, which I will come to at the end. But hopefully one of you all could tell me the aha moment before, right? Good. So we have phi from Q. You remember what Q is, right? So we have this group. We have set of real numbers, and they multiply. The operation is multiplication. So we have one group, we have 2 groups. Yes, and the homomorphism I came up with is phi of A equals to A squared. So we want to prove first that this is a homomorphism. Right, so we have to prove that phi is a homomorphism. Yeah, so we'll do it together. So we want to show that phi of AB, so it's multiplied, so phi of AB is eventually, we want to show it's phi of A, but it's still multiply, yes? Phi of B. So phi of AB is xy, right? So x, y, b in Q. Then phi of xy is xy all squared, which is x squared by y squared, which is phi of x, phi of y, yes? Therefore, phi of x, y equals to that for all x, y in Q. Hence, phi is a homomorphism. Everybody's okay? Nice. What is the identity in R? 1, right? So E is 1. What is the identity in Q? 1. Same identity, yes? That's fine. What elements in Q will be mapped onto 1. So we're trying to find the kernel. Remember, the kernel are those elements in the domain such that f of those elements equals to 1. So, I mean, it's simple, right? So phi of x equals to e in h, well, in R, which is 1. So x squared equals to 1, right? Which would be x equal to plus or minus 1, right? Yeah. So kernel of f of phi equals to, it's a set, right? Remember, it's a set. The set of elements would be 1 and minus 1. Anybody has any questions? Everybody's good? Nice. So what this says now is this set Q. So remember, Q would be all irrational numbers. It would be P on Q, where Q is not equal to 0, such that P and Q are integers, yes? So basically all the numbers, all the fractions, all the numbers that are not complex and not irrational. So no pi, no square roots, no e's, yes? Nice. So we have this set here. Well, we have Q on 1 minus 1, and this is isomorphic to the range of R. So what is, to see this a bit better, because Q has everything, I'm just going to take some values for Q so you can understand what's going on, right? So we'll take 0, well, sorry, yeah, we take 0, we take 1, we take 2, take minus 1, we take minus 2, minus 1.5, 1.5. Everybody's okay? So right, so this over this gives, so if I were to just not take Q, but I'm just taking that representative set, right? It's really and truly all the numbers in between there, right? All the rational numbers. So no square root of 2, etc. So let's just say we have minus 2, minus 1.5, minus 1, 0, 1, 1.5, 2, over 1, negative 1. What does this give? What does this yield? This over this. Well, the factor group of Q by 1 minus 1. Remember, these are cosets, yes? So it's this, which is the n. So remember, it's normally G on n is the set of cosets of n by an element G in G, yes? So in this case, my n is 1 minus 1, and I'm taking elements in G, which are small g's, which are these numbers, and I'm multiplying them. Yeah? So if I take minus 2, what do I get? I'm going to get minus 2, 2, yes? If I take 1, sorry, so this is the big set. So if I take minus 1.5, I'm going to minus 1.5, 1.5. If I take minus 1, minus 1, 1. If I take 0, I'm going to get 0. Well, 0, 0, right? But 0. 1. If I take 1, I'll get 1 minus 1. If I take 1.5, I'm going to take 1.5 minus 1.5. If I take 2, I'm going to get 2 minus 2. Y'all okay? Yes? Nice. But if we realize we have minus 2, we have minus 2. So we just need 1, 2, minus 2. Then we have 1.5, negative 1. We have negative 1.5, 1.5. We have negative 1.5, 1.5. You're seeing the repeats, right? So this here is the same as this. This is the same as this. This is the same as this, yes? So we have negative 1.5, 1.5. We have 1, minus 1. And we have 0. Everybody's okay? So what this maps onto is this maps onto the range. So what would be the range? So what element would 0 map onto? So I'm running out of space, so this is going to be on the next line, right? So what element would 0 map onto? 0 would map onto 0 squared. What element would these map onto? 1, right? Because, okay, if you square 1, if you square 1, you're going to get 1. If you square minus 1, you're going to get 1. So this would map onto 1. What element would these two map onto? 1.5 squared. 1.5 squared. Yeah, this is mapping, right? Is the mapping. Is the mapping, right? You all follow, right? Right, so what this says is that this set, but obviously all things are missing here, right? I wrote it in the reverse order. So 0 would map onto 0. The set 1 minus 1 would map onto 1. The set minus 1.5 would map onto 1.5 squared. The set 2 minus 2 would map onto 2 squared, and so on. You all seen it? Yes? Nice. And the beautiful thing about this term is that we know it maps onto it. We don't have to go and prove that it maps onto it. That is the term. Once we have a group and we have a homomorphism, then we know the homomorphism over the kernel. Sorry, the domain of the homomorphism over the kernel of the homomorphism maps onto the range of the homomorphism. You follow? So we know this for sure. We don't have to think about what is the mapping. We don't care. But it'd be nice if we know the mapping though. So anybody, you all follow what's going on? I will remove this just to write it and analyze it a bit more. So what it says basically is that 0, 1 minus 1, 2 minus 2, dot dot dot, n minus n maps onto, yeah, this would map onto anybody? Anytime soon? 0 maps onto? 1 map, this set maps onto? This set maps onto? This set maps onto? You follow? Right. Now what does isomorphic mean? Isomorphic, for all intents and purposes, means that the first set acts exactly the same as the second set, yes? And we know if something is isomorphic to something else, it's a homomorphism, it's 1-to-1, and it's on-to. Everybody's okay. So we can see the 1-to-1 property that 0 will map onto this, 1 will map onto that. You are following? The onto. So if we have any n, then what would have been mapped onto that? N minus n, yes? Good. But look at this. You have to find how many elements does this set have? This set. This set. This set. You have to find out strange that all these have 2 elements and this only has 1 element. It doesn't look odd? Like just so let's just go down again. These remember we have the factor group of G by n, yes? These are what? Cosets, right? This is n, where n is the kernel, by an element G. And G is in G, yes? And I don't know if you all would remember, but this is a coset, yes? So G1 is a coset, n, G2 is a coset, and so on and so forth. There's a theorem which says that all cosets must have the same number of elements. Yes? So, this is a coset, and this is a coset, and this is a coset, and this is supposed to be a coset, right? But it doesn't make sense because this one has one element. So if that has one element, and we know that all cosets must have the same number of elements, then something is wrong here. You all follow? So what could be wrong? Obviously 0 is not supposed to be there. Why is 0 not supposed to be there? Anybody could come up with some idea how we know 0 is not supposed to be there? Why is 0 not supposed to be there? How we can justify 0 not being there? That's like 99.9% correct. You know what you're saying, you just don't know how to explain it properly. R is not a group under multiplication because 0 does not have an inverse. So these two at the start, when I said these are groups, instantaneously, no, say those are not groups because 0 is there and 0 does not have an inverse. So this is not supposed to be Q, this is supposed to be Q minus singleton 0. Similarly here. You all follow? And this here would give an idea of the structure of groups. It's a very small or minor example, but you know, hey, well, you know, this group has a weird structure. It's like, wait, now all the elements have 2 and 1 have 1, something is wrong there. That structure doesn't look good. And then you go back and you say, well, okay, well, this is something wrong here. And you look back to see your question if everything was okay with your question. You all follow? Way boy, sir. That was the aha moment. So that is what this was for. Because I didn't want to give the question properly, because I wanted to show, A, we have a coset that has 1 element and all the other cosets have 2 elements, so something is definitely wrong, and then go to figure out the answer. If I were to form a mapping though, so if I truly wanted to prove the isomorphism, could you all think about a mapping that would work? So let's just modify, so the question, I'm modifying the question, right? This is not supposed to be here, so 0 is not supposed to be here, so that's the answer. Everybody's okay? So the second part, which I'm just adding because I think it's a good practice, we need to show that, right, so we just want to recap and I want to go through step by step to show you what goes on in the isomorphism theorem. So this is not necessary, but I mean, we now introduce the theorem, you want to make sure it's working on what does it really do, you know, on a concrete level. So just to recap very quickly, we have a set Q minus R with normal multiplication, set of rationals, and this is mapping onto, we have another group, sorry, so we have 2 groups, one group and the next group, R minus 0. Remember, we don't have 0 because there's no multiplicative inverse of 0. So that's why we remove 0. Now we form a function, phi, and we know from before, last example, that this was a homomorphism defined by phi of an element A is A squared. So this is a homomorphism. And the kernel of this homomorphism, so the kernel of phi, was 1 minus 1. That is where we ended. Now I want to show that the factor group of Q minus 0 on the kernel of phi is isomorphic to the range of phi. So we'll go through, make sure we understand what it means. So in other words, I want to show that the factor group of Q minus 0 on the kernel of phi is isomorphic to the range of phi. Now let's just understand what the range of phi is. Now this is important. So phi squares the elements from Q. So all the elements A are taken from the first group, which is Q, and they are squared. So the range would be all the elements Q that are in Q squared. So in other words, it's the square of the non-zero rational numbers. I hope you all understand that, right? So it's the square of the non-zero rational numbers. So this here, I'm going to call it Q bar. And this is actually the square of the non-zero rational numbers. How does this look? Now from the last example, what we now did, we understand that the elements in this here are actually elements of this form, A minus A. So for example, we can have 1 minus 1, we can have 2 minus 2, and so on. What I'm going to do for ease of analysis notation, I'm just going to call that set X. I'm going to let X be the set of 1 of A minus A negative A, where A is in the set of non-zero rationals. Now I want to show that this set X is isomorphic to Q bar. Now remember what Q bar is, right? Q bar is the set of non-zero rational numbers. So we get. So this is basically my question. Now to show this, I need to do 3 things. I hope you all remember the 3 things. Huh? 1, homomorphism. 2, one-to-one. And 3 is onto. Onto is kind of obvious because we have formed the set in such a manner, because we are taking Q bar, which is all the elements that are used, right? So it's not necessary to do it. I might do it, I might not do it. We'll see how it goes. So with that being said, now we want to show homomorphism. So the general point for homomorphism from before is, first we need a mapping. I'm going to use similar mapping. So f of an element in X. So remember, we want to form a homomorphism from X to Q bar. So in other words, I'm going to call this homomorphism X. F goes from X to Q bar, such that f of an element in X, is what? A minus A equals to A squared. So this is my mapping that I want to show is one-to-one, onto, and is a homomorphism. So this is important. We will box this off. So now we are going with homomorphism property. Basic definition of a homomorphism. We know if F is a homomorphism, we take 2 elements. So let's just call this multiply in the first group. F of AB, we need to show that this is F of A, and say multiply in the second group. This is what I want to show. We need to relate this to our question. For this question now, my elements are really sets. So this becomes, let me just make a little space here. So this becomes, I want to show that F of 2 elements, which would be A minus A, and I'm going to use the multiply, so let's just use normal multiply. We'll get to this multiplication in a while, of B minus B equals to F of A minus A multiplied by F of B minus B. That is my goal. Now, these elements here are cosets. You remember that we're dealing with cosets because they form a group. And there's a special coset multiplication defined by, I hope you all remember, n of G1, so if this is the first coset, N is the normal subgroup and G is the element, multiply by N of G2, this is N of G1, N of G2. This is the definition of coset multiplication. We are dealing with cosets, so therefore we need to use this definition. So let's go. I'm just going to take inside here and simplify. So what will this become? So we have F of, I'm going to write this in a way that the normal subgroup is recognizable, which is simple. We just extract 1 minus 1, right? It's simple, it's straightforward. So this is really 1 minus 1, which is really the kernel, which is the normal subgroup, by what element will it be? A, right? It's obvious. Multiply by this here, we extract it, so 1 minus 1 by the element B. Everybody's okay, you're all seeing this. So this is really, this is my N, and this is my G1 is A, this is my N, and G2 is B. And that will give me N, G1, G2. So this gives, I'm going to just write in the next line, F of open brackets, N, A, B. Yes. And this simplifies to, we multiply F of AB minus AB, set brackets. Simple enough. And then we apply the homomorphism. So we have defined F of A minus A as A squared. So this is F of something minus something. This gives something which is AB all squared. But we're not finished. Our goal is to show that that is equal to F of A minus A and multiply by F of B minus B. So this here, we can actually write this as, I'm a bit pressed on space, so I'm just going to go here, equals to A squared by B squared, simple algebra. And this A squared could be written as F of, yes, you all guessed it, A minus A by, and this is the operation in the second group, which is the same multiplication, F of B minus B. And that is my answer. So therefore, we have started with F of a product, and we've shown that that is equals to the product of the two F's. So we started here, and we finished here. So therefore, that completes the homomorphism proof. It wasn't so bad. Yeah. That okay? Lovely. So now we're going to go on to one-to-one. Let me just erase the book. Right, so we want to continue with one-to-one now. Basic definition for one-to-one that we all know. One-to-one would be if we have two elements, x and y, in our domain. If f of x equals to f of y, if this happens and it implies that x equals to y only, then we know it's one-to-one. So we need to relate this to our question. So again, we are going from x to q bar. X is really the factor group of q minus 0 on the kernel. So again, the elements of x would be these. So we need to take two elements from here, and then we need to apply the homomorphism and then, well, the function, and then show that we get back the same element. So an element in x would be, so representative elements in x would be same thing from before. We'd have A, negative A, and we'd have B, negative B. So what we want to show is f of this equals to f of that. If this happens, then this set is equal to this set. It's just a matter of algebra. So if this happens, then we define the homomorphism. That gives A by A. So this gives A squared. Sorry, how we define the homomorphism? It gives A squared equals to B squared. Solving this gives A equals to plus or minus B. So we need to go through these two cases. So in case 1, if A equals to B, then remember we need to take the element, this element. If A equals to B, then A negative A is equal to, if A is equal to B, then this gives B negative B, which is fine. Case 2, if A equals to negative B, I know it's a bit baby steps I'm going through with you all, but I just want to do it for completeness, right? Because it's really simple. Then A negative A gives negative B, negative of negative B, which simplifies to negative B, B. And because the set is unordered, this is B, negative B. So in both cases, we know that A negative A simplifies to B negative B. So they're equal. We just need to conclude with a statement saying that. So I just want to conclude in both cases, since in both cases A negative A equals to B negative B, F is 1 to 1. Straightforward. The last thing is onto, which again is straightforward. It's obvious from the way we define the function, because we are going from X onto Q bar, and Q bar is the set of squares of the rationals. Because remember, we're going from Q minus 0 into R minus 0, and we're just taking the range of this, and we call the range of that Q bar. So it will be onto, but if you want to see something mathematical, this is how it would be. So we would take an element in our codomain, which is Q bar. So let P be an element of Q bar. Then P equals to Y squared for some Y in Q minus 0. Singleton 0, because that's how the first homomorphism was defined. Therefore, F of, can you all guess it? What would give me Y squared? F of Y minus Y would give Y squared, which is P. Follow? And we know Y minus Y would be in X. This is kind of obvious, but just to state the obvious, would be in X. Right? Because Y would be in Q minus 0, and X is the set of cosets. So this would be in X. Hence, F is onto, and that's it. So we have shown homomorphism 1 to 1 and onto. Therefore, it works. It's isomorphic. And we didn't need to go through all this because that's what the first isomorphism theorem says. If you do have a group and you have a next group and you form a homomorphism from one group to the next group, the factor group of this on a normal subgroup, well, in this case, the kernel, would be isomorphic to the range. And that's it. I mean, it's beautiful. So let's go on to example number 2 now, which is my favorite example. we are on our second example, and this is one of my favorite groups. I think you all should know what it is by now. Anybody can make a guess? Yes! 1 minus 1 I minus 1. So let G 1 minus 1 I minus I, and we are going, so our homomorphism, say phi is from G to the range of phi, such that phi of x is the norm of x. So it's the norm of x where right, so I just changed around some variables there. So phi of z equals the norm of z to complex numbers, where if z is a plus ib, so it's standard definition. So we want to prove that phi is a homomorphism. So we know, so now, oh, in fact, no, wait, y'all try. Yeah, so this is the goal. I want you all to figure out for me what would be the sets. So, yeah, by yourself. So you all need to figure out G on the kernel of phi isomorphic to what? To the range of phi. So you all figure out how this would look, figure out how this would look, figure out how this would look, and then simplify what this would look as. And yeah, just like we did in the example before. Take your time, go through. Shouldn't take too long, it's a simple set, only 4 elements. You can just use the property from complex numbers, the norm of product. Don't worry with us. Calculus. Let A be element of G. Now phi of AB, equals to, you'll go from there. It's always the same. We take 2 elements in my domain. This is the length of AB, yes? Which is the length of A, norm of B. Just take that straight from complex numbers, right? Which is phi of A, phi of B, right? This is an exercise in calculus. That's not my concern here, right? You follow? Hence homomorphism. So prove 1 to 1. So we've done the first part. So now we need to do is find what elements are in the kernel of phi. So what is the kernel? The kernel. What is the kernel of phi?
1 minus 1.
The kernel is G, which is not what I intended. So let's just change it up. So let's just use the same function from before. Oh, I can't believe I did that. So let's use a squared. So this is a homomorphism, yes, from before. So new question, exact same set G. Right. So now we have our homomorphism as psi of A is A squared instead. So the kernel of this would be what? So instead this has to change. So the kernel of psi is, right, which should imply that the kernel of psi is 1 and minus 1. You understand that? Remember, the kernel is all the elements in the set that maps onto the identity in the next set, and the identity in the next set is 1. So 1 squared is 1 and minus 1 squared is 1, but I squared is minus 1 and minus I squared is minus 1. You all seen it? So just to make sure. So these two are in the kernel. You follow? So now what we want is G over the kernel of psi is isomorphic to the range. So find out what these things look like. That's the next exercise. So we know what G is, we know what kernel is. Find out what this looks like and then divide this and find out what the quotient group is. so G is 1 minus 1 I minus I, and the kernel is 1 minus 1. So this, I'm just simplifying this here. So remember, the factor group G on n of G by n, the elements of this, we take this set here and we multiply this set by each of the elements in G. Yes? So I were to take 1 and multiply it by this, I'm going to get 1 minus 1. 1 minus 1. If I take minus 1 and multiply it by this, I'm going to get minus 1 by minus 1 is still 1. Minus 1 by 1 is still minus 1, yes? Sorry. Yeah, so when I take 1 and multiply by this, I get this set. When I take minus 1 and multiply by this, I get this. So it's the same thing. That's why I didn't write it twice. Comma. So this is a set. When we take I and multiply by this, we're going to get I minus I. When we take minus I and multiply by this, we're going to get minus I. And when we take minus I and multiply by minus 1, we're going to get I. So it's the same thing. So this here would be the factor group of G by n. In this case, G is G and n is the kernel. Yes? And the range, so this is isomorphic to the range. The range would be all the elements that are mapped onto, yes? What would be the range? Well, in this case, we actually did it, right? I did this. So these are all my elements, and they are mapped onto 1, 1, minus 1, and minus 1. So it just mapped onto 1 and just mapped onto minus 1. So this is isomorphic to 1 minus 1. You all follow? So if I were to make some analogy, this here would be linked with this, and this one would be linked with this. You all follow? Good. Now, the beauty of this theorem, which is a big thing, is by using this theorem, we can analyze properties and structures of groups in an easier way. So in other words, if we know, okay, so our initial set G has how many elements? 4 elements, yes? But our factor quotient group of G by the kernel has how many elements in it? Only 2 elements. So in other words, what we are saying is that the properties that holds with this, let's just say coset, and would extend to G, and that holds with this would also extend to G. So in other words, we could only consider 2 cases. We analyze this and we analyze this, and then we know that this gives rise to a next half of the group, and this gives rise to some other properties, rather than thinking, oh my god, we have 4 different cases to analyze. You all follow what's going on? So that is what it does. And because it maps onto the range of F. Yeah, okay, I'll leave it there. So let's just say we have a group G that has 1,000 elements in it, and we have a group H that has 500 elements in it. Yes? How many elements would G on H have? Two. You understand? So now this factor group here would only have 2 elements. Now remember, in order to construct this has to be normal, etc. Right? The point is, I'm just trying to give you all an understanding of why the theorem is so important, right? I'm not going into the specifics of this has to satisfy everything. This is the long story, very short. You have an element G, and you have you have you have a group G and you have a subgroup H that has 500 elements, then you know this factor group would have two elements in it, yes? So in other words, if we found out what these two elements are, which we could find out, then we just need to analyze, say one of the elements is A and one of the elements is B, analyze all the properties of A, analyze all the properties of B. Once we know all the properties of A and B, then we know all the properties of the group. Which means that any elements in this group will either have this set of properties or this set of properties. You understand? And that's why it's so important. So you can take a big group and then map it back to a smaller group and keep on doing that and keep on doing that and get properties. Which is like a big thing. Huge. Anybody has any questions?